శ్రీ ముత్తవరపు వెంకటేశ్వరరావు కాలేజ్ ఆఫ్ ఇంజనీరింగ్ అండ్ టెక్నాలజీ 2008 లో స్థాపించిన కళాశాలలో NBA, NAC A గ్రేడ్ మరియు ISO సర్టిఫికేషన్ సాధించిన మొట్టమొదటి కళాశాల శ్రీ ముత్తవరపు వెంకటేశ్వరరావు కాలేజ్ ఆఫ్ ఇంజనీరింగ్ అండ్ టెక్నాలజీ త్వరలో అటానమస్ కాబోతోంది.
2014లో ISO గుర్తింపు, 2015లో రాష్ట్ర ప్రభుత్వంచే A గ్రేడ్, 2016లో NAC A గ్రేడ్, ఇప్పుడు NBA సాధించిన సంస్థ శ్రీ ముత్తవరపు వెంకటేశ్వరరావు కాలేజ్ ఆఫ్ ఇంజనీరింగ్ అండ్ టెక్నాలజీ.
Good afternoon, students. In the last class, so we have discussed about the stability of an op-amp, and in this class we are going to discuss about the frequency compensation of an operational amplifier. So in this, so what are the different frequency compensation techniques are there? We are going to observe that what are the different frequency component techniques are there, and then we are going to discuss about that frequency component techniques. So why we are going for frequency compensation? So why we are going for frequency compensation means in several applications of operational amplifier, we need a large band. So the op-amp must operate in a large bandwidth, but it may not be possible for a practical op-amp as there is a effect of the three corner frequencies as we have discussed in the last class. So for that reason, we are going for improving the bandwidth as well as maintaining the gain. So for maintaining the gain and bandwidth, so we are going for this compensation techniques. Okay, so this compensation is of two types for our operational amplifier. So one is external compensation. That means we are going to connect different devices external to the operational amplifier. That means we are going to connect either a resistive or capacitive component externally to the capacitor. So by connecting to the operational amplifier, so by connecting these external components for an operational amplifier in the output session, so for compensation techniques are of two types: external frequency compensation and internal frequency compensation. So external frequency compensation comes and when we are connecting external components to this operational amplifier. So we are connecting the components which we are considering the passive components external to the operational amplifier. And coming to the internal frequency compensation, in the op-amp manufacturing itself, we are providing a compensation technique. So these two techniques we are going to observe now. Now first we are going to discuss about external frequency compensation. So what is this external frequency compensation? This frequency compensation can be achieved by adding compensating network to the operational amplifier. So by adding compensating network means we are going to add the passive components to the operational amplifier such that the frequency response, those components are going to improve the frequency response of the amplifier, operational amplifier. So it not only increases the bandwidth, that means it is going to increase the bandwidth, and also it provides a lower closed loop gain. So loop gain will be also less when compared when we are going for this compensation. And as we have discussed in the last class, there will be three roll-offs at three corner frequencies. That is, at first corner frequency, after the first corner frequency, the signal is attenuated by minus 20 dB per decade, and at the second corner frequency, the signal is attenuated by minus 40 dB per decade, and at third corner frequency, after third corner frequency, it is increased by minus 60 dB per decade. So for that reason, by introducing this compensating network, the decay will be, that means the attenuation of the signal will be constant. That is my 20 dB per decade. That is minus 20 dB per decade. That roll off takes place with constant attenuation. There will be no change in the attenuation, 20 dB, 40 dB, 60 dB, like that. There will be only a single attenuation component, that is minus 20 dB per decade. So for this, in this external frequency compensation, there are of two types of compensating techniques. One is dominant pole compensation, and another one is pole zero compensation. So what is this dominant pole compensation? And what is the pole zero compensation? Now, coming to the dominant pole compensation, we observe here. Here you can see the thing. So this is the dominant pole compensation. Here you can observe this is the circuit we are using for dominant pole compensation. So in this circuit, you can observe here we are giving input to the operational amplifier, and we are not taking output at the output of operational amplifier. We are giving this output to a compensating circuit, that is a combination of R1 and C1. Nothing but RC. RC component is added, in which R is connected in series, and C is connected to shunt. So this RC component is added to this operational amplifier. When this RC component is going to be added, then there will be a roll off. So here you can observe that roll off frequency. So here you can observe that by adding this RC component, actual gain of the operational amplifier will be like this, which is having three corner frequencies, F1, F2, and F3. And when we are adding these two components, that is R1 and C1, so the frequency, the gain is going to fall from point Ft to F1 directly with minus 20 dB per decade. This attenuation is nothing but minus 20 dB per decade. So what happens by adding these two R and C components, we will see. So what happens? So when RC is added, then what happens when RC is added? What happens? So here you can observe from this. So A dash here, A dash will be the gain of this circuit. So A dash will be gain of this circuit, means along with this RC component also. So along with RC component, we are going to consider the gain. So as the gain of op amp is, as the gain of op amp is, as the gain of op amp is nothing but A. And here we are having the gain of this circuit, which is nothing but output by input, which is nothing but we are going to consider it as A dash. We are going to consider that as A dash, which is given by V out by V in. That is nothing but here we are going to write it as V naught by Vi. So which is equal to, so this is the gain of our operational amplifier. So which is given by the gain of operational amplifier into the reactance of the capacitor. So which is nothing but minus j by omega c, and the resistance, the total resistance present in this part, r minus 1 by j omega c. So here in the place of r1 and c1, we are going to write r and c. No change in that, just we are going to write here r and c. It is nothing but we can write r1 and c1 also, no problem. So this becomes this is the concept we are going to get. Then what happens mm, to this, as we know that which is this is further equal to a by 1 plus j into f by ft. So by solving this equation, so how we are going to solve this equation? So we are going to we are going to take LCM of this omega c. Then what happens? by taking LCM here, R into omega c. So R will be multiplied with omega c and J will remain same and divided by omega c, and here minus J by omega c. This omega c and this omega c will get cancelled each other, and denominators, both denominators will get cancelled each other, and we can write a minus j as we can, so we can write minus j as 1 by j. So j again, becomes into the denominator section, and here also the j comes to the denominator section, and when j comes to the denominator section, we are going to multiply it with the rc. So j omega rc minus, here it will be 1 1 j omega rc minus 1 divided by j omega rc j minus j omega rc minus 1 divided by j omega c. Okay. This j omega c and this j omega c will get cancel each other, and this minus and this minus, we are going to multiply the equation with the negative minus, and then it becomes positive. So a divided by 1 plus j into f by ft. So where f is the frequency due to, where f is the frequency, fd is the frequency component which is due to 2 pi rc, and here in the place of omega we are going to write 2 pi f. So this is this frequency, and this is nothing but the frequency which is introduced by this rc components which we are adding here. You can see here which we are adding this rc components is going to introduce this rc, and is going to introduce this ft. So because of this fd, so fd, that means this point is chosen such that by selecting proper r and c components, nothing but we can adjust this fd by adjusting r, or we can adjust this fd by adjusting capacitance one. Both, we can adjust both, or we can adjust any one of the component. So here mainly we are going to adjust the capacitive component, so for maintaining this fd, and fd is also selected such that this fd is going to compensate, is going, fd is selected such that compensative transfer function, that is a dash, this compensative transfer function is a dash, passes through a dash, this is nothing but this is compensative transfer function, passes through the 0 dB, this is 0 dB, passes through the 0 dB at frequency f1. That means we are going to select this fd such that it is going to pass through this function, is going to pass through the f1 at 0 dB, f1 at 0 dB frequencies with a slope that is minus 20 dB per decade. And finally, when you are considering three frequency components, as we have seen here in this graph, we are having three frequency components, f1 and f2 and f3. So we are considering those three components, and we can write our transfer function. Now our transfer function is going to become a dash, which is equal to open loop voltage gain, that is AOL divided by what we are having here. A is nothing but AOL, so AOL divided by 1 plus j by fd into 1 plus j by f by f1, f by f2, and f by f3. So these are three corner frequencies. Along with these three corner frequencies, we are going to use another RC network that compensates our op-amp operation, such that it provides the response like this. So this is the gain frequency response for dominant pole dominant pole frequency compensation technique. So this is how, so we are going to, here you can see one thing. So here fd is going to pass at f1. So now the bandwidth, you can see up to here the gain is constant, and after that the gain is going to fall by 20 dB per decade. After that the gain is going to fall by 20 dB per decade. So here you can see the gain has been reduced. That means the bandwidth. Sorry, the bandwidth. So the bandwidth has fallen up to here. So before that the bandwidth is here, but by introducing this dominant rule, the bandwidth has fallen. But we can overcome the performance. We can overcome these three attenuations. So this is how the dominant pole is going to provide. So in this, we are having a drawback that it reduces the open loop bandwidth drastically. That is nothing but so here you can see it reduces the open loop bandwidth drastically. But the noise immunity has been improved for this circuit. For the circuit, what we have discussed, this the noise will be improved. The noise will be improved, and then mm, by choosing C value, proper C value, we can select the frequency of T. So this is the drawback is it reduces the bandwidth, what we have discussed now. And then coming to this is about the dominant pole compensation technique. And coming to another technique, the another technique is nothing but pole zero compensation technique. So in this pole zero compensation technique, the gain is altered by introducing both the pole and zero. The gain is going to be adjusted by introducing pole as well as zero. And we are going to keep one thing in mind here, that is the zero which we are introducing will be should be the zero should be higher than the pole. The zero frequency should be, that is what we are going to select, the zero frequency that should be higher than the pole frequency. So by adjusting here, what we have observed here in this diagram, you can see operational amplifier. What is the difference between the previous dominant and pole zero compensation? So here in series to the capacitor, shunt capacitor, we are adding a resistor R2. So that is only the difference between a dominant pole and pole zero compensation. That is only a small difference. So by introducing this R2, we are going to introduce a pole as well as a zero, one pole as well as zero. And then the transfer function, this is the circuit in which the transfer here V in is the input and V naught dash is the output for operational amplifier, and V naught is the output for this total circuit. And when we are considering the gain of this total circuit, then we are going to calculate it by V naught by V in, nothing but when we are considering the gain of op amp, that is nothing but V naught dash by V in. So by considering this, by solving this, we have that we are going to discuss as let A1 be the transfer function of compensating network. So the transfer function of compensating network be A1. We are going to consider the transfer function of compensating network is A1. Then the output will be V0 by V0 dash. So let Z1 is equal to R1. So where we are going to take this Z1? So we are going to consider the impedance, because here we are going to consider it as Z1. So here we are going to consider it as Z1 and this as Z2. We are going to consider this as Z1 and this as Z2. So when we are considering these two, then our equation Z1 is equal to nothing but so Z1 is going to become Z1 is equal to R1 and Z2 is equal to R2 minus JXC2, because having in the Z2 we are having the capacitive component also. Z2 is equal to mm, R2 minus J2XC. And so where minus JXC2 can be written as 1 by J omega C2 also. So by solving that equation by voltage division rule, we can write A1, the gain A1 is equal to Z2 by Z1 plus Z2. So overall gain, this is overall gain of our circuit. So which is given by R2 minus JXC2 divided by R1 plus R2 minus JXC2. So by solving this equation, so we are going to get A1 is equal to 1 by J 2 pi F R2 C2 and 1 by J 2 pi F R1 plus R2 into C2. So this is the final equation we are going to get by solving this. So this is the final gain we are going to get. So that is 1 plus J 2 pi Fc into 2 pi Fc2 R2 uh, by 1 by J 2 pi F R1 plus R2 into C2. And then we know that now let F1 is equal to, so F1 is the frequency, that is 1 by 2 pi R2 C2, and F0 is equal to 1 by 2 pi R1 plus R2 into C2. So let us consider, we are going to consider it as F1 is equal to 1 by 1 by Z 1 by 2 pi R2 C2, and F0 is equal to 1 by 2 pi R1 plus R2 into C2. So then our transfer function A1, our transfer function of the circuit, that is which we are considering the pole zero compensation circuit, that is A1 is equal to 1 plus J into F by F1 divided by 1 plus J into F by F0. Then this is the transfer function of nothing but this is the transfer function of our compensated network. So this is the transfer function of our compensated network. So when we are considering this transfer function along with our op amp transfer function, then the equation will become like this. So A1 is equal to, as we know that A1 is equal to AOL into AOL divided by 1 plus JF by F1, 1 plus JF by F2, 1 plus JF by F3. Yes, this is actual equation, nothing but so here I will show you. So, so this is the actual gain equation for our operational amplifier, and for this, so this is the actual equation for our operational amplifier. Then what we have get here, 1 by this is what we have obtained here, and this is the gain of the compensative network. Then we are going to combine these two gains, then we are going to obtain this equation here. So then we are going to obtain this equation here. So by obtaining this equation, you can see here in this equation, in this equation, we can cancel these two components. That is 1 by 1 plus J into F by F1 and 1 plus J into F by F2. These two components will be cancel each other. And finally, so we are going to get the gain which is equal to AOL divided by, that is the gain, final gain is equal to, so final gain, so what is the final gain we are going to get? AOL, final gain we are going to get AOL divided by, so we are having only these three components, 1, 2 and 3, that is 1 plus J F by F naught, one component, and another one 1 plus J F by F2, and another one is 1 plus J F by F3. So these three components we are having. So finally, when we are going to introduce when we are going to consider the pole zero compensation, so mm, we are going to observe this equation AOL divided by 1 plus JF by F naught plus 1 plus JF by F2 into 1 plus JF by F3. So where 0 less than F naught frequency less than F1 less than F2 less than F3. So by here we are going to consider one thing such that the composite network produces a zero at first corner frequency f1. So the compensated network produces a zero at first corner frequency f1, so which is going to produce a zero at first corner frequency f1, and uh, f naught is equal to omega naught divided by 2 pi, which is going to select it such that compensated transfer function, this is the compensated transfer function, which is going to pass through 0 dB at the frequency f2. So see here, in dominant pole compensation, we are going to select such that the compensated transfer function is going to pass through f1 there. So whereas here we are going to select such that compensated transfer function is going to pass through f2. Now, so we can see here the bandwidth has been improved. So now the bandwidth is up to f2, our op amp is going to work. So we can say that the bandwidth has been improved, and this is the one thing. And by we are going to select the resistance values. That is, here we are having two resistance values, such that we are going to select that resistance values which we have considered here. Here you can see these resistance values R1 and R2. So R1 and R2 is selected such that R1 and R2 is selected such that the component R1 and R2 is selected such that mm, R2 must be very much greater than R1. So we have to select the R1 and R2 components such that R2 value must be very much greater than R1, so that the factor becomes 1, and when it is multiplied with the gain, it is negligible. So here we have to keep this concept also in our mind when we are considering this pole zero compensation. So if there is no pole added at F1, the response would have change in the curve. So what is the, now we are going to observe what is the difference between this pole zero compensation and the dominant pole compensation. So when we are going to observe the difference between these two, so uh, here when we are going to consider difference between these compensating techniques, so you can see here difference between these two compensating techniques. So you can observe here. Okay, okay. So you can observe here. So when you are going to observe this, you can observe this one thing, that is the pole is this is the dominant pole. This is due to dominant pole compensation, and this is due to pole zero compensation. So by observing this graph, you can see that pole zero compensation, the bandwidth has been improved. So here, op amp is going to operate from this frequency to f2. Here you can see in dominant pole zero compensation, whereas in dominant pole compensation, the bandwidth is less when compared with the pole zero compensation. So this is what we have observed in these two compensating techniques. And coming to the third one, that is internal compensation. of an operational amplifier. So in internal compensation of an operational amplifier, so we are going to consider here, so this is the internal compensation of an operational amplifier. So in internal compensation, so for an operational amplifier, we are going to introduce the capacitance internally. We are going to introduce the capacitance internally, and then by introducing the capacitance internally in the op amp itself, the frequency response can be improved. The frequency response can be improved. So generally, so when we are going to use this type of op amps in instrumentation applications, so there we are going to use internally compensated op amps. So MUS 741 op amp is internally compensated with the capacitor uh, C1, with capacitor C1 of 30 picofarads, and open loop gain of 20 dB. And this op amp has 1 megahertz gain bandwidth. So some of the op amps which are internally compensated are, so what we are using in our laboratory is nothing but the internally compensated op amps, that is MUA 741. So as we have discussed in our first classes, MUA was fabricated by Fairchild. LM741, which is fabricated by mm, National Semiconductor, like that LM107, LM112, and MC558 are the different types of op amps which are internally compensated. Which are internally compensated. So this is about the internal compensating technique for an operational amplifier. And then internal compensation technique for an operational amplifier. So this is a internally compensated technique. So, so by introducing internal capacitor, so this will be the internal compensated technique for an operational amplifier. So by introducing that, the frequency response curve will be like this. So we can observe this frequency response by taking the op amp and by connecting the sinusoidal wave to that, and by increasing the frequency and maintaining the input voltage constant, we can observe the op amp response, frequency response. So this is the frequency compensation technique. Thank you, students.